Alrighty guys, we're going to go ahead and look over our quiz energy basics. So the first question is asking us to match the type of energy with its definition. First thing we're going to notice is the gravitational potential energy here. Well, we said gravitational potential energy is energy that deals with height, right? Or in other words, an object's position in the air. The next one is kinetic energy. Kinetic means motion, so this is going to be the energy due to motion. Next, we have thermal energy, and thermal energy is energy that results from friction or air resistance. We can see it with cars, right? As cars drive, if we were to stop very quickly, sometimes if you look behind you, you'll notice that there's smoke coming from your tires because the friction is generating thermal energy. Lastly, we have elastic potential energy, and elastic potential energy is just energy that deals with springs or stretchy objects. Think about elastic bands in sweatpants, right? Those are stretchy objects. All right, next one, match the energy when it is zero. Well, on the first page, we just said that gravitational potential energy deals with height. So when would that be zero? When we don't have any height, when we are on the ground. We consider the ground to be zero height. Kinetic energy, we said, was the energy of motion. So when is the energy of motion zero? When we are at rest. When we are not moving, there is no motion. Thermal energy, we said that deals with friction and air resistance. So it makes sense that we're not going to have any thermal energy when we don't have any friction or air resistance. So this is all a theoretical type thing, right? Because in the real world, we have friction and we have air resistance, but we're going to pretend that we don't, therefore eliminating thermal energy. And lastly, elastic potential energy, we said deals with stretchy things. Well, when is there no potential energy? When we are not stretching those. Think about, right, those rubber bands, how sometimes your friend would take it, pull it really far back, and maybe hit you with it, all right? You were probably terrified the further your friend stretched that rubber band because you knew that it was going to hurt more and more. But if they don't stretch the rubber band, or possibly like you walk past a desk and there's just a rubber band sitting there, you're not worried that that rubber band is just going to fly off the desk at you and, hit you or something, right? Because if it's not being stretched, it's not going to have any energy. All right, energy cannot be created or destroyed. True, true, true. This is something that we have talked about before and we will continue to talk about. Energy is only able to be transferred. You cannot create your own energy. It has to come from somewhere and it has to go somewhere when you're done. Like we just said, energy can be transferred from one form to another. For example, we could transfer from gravitational to kinetic. True, right? The only way to have a type of energy is to transfer it from one form to another. Gravitational potential energy is coming from somewhere. Kinetic energy is coming from somewhere. All of these different types of energies are just being taken from a different type of energy and transferred into the one that we need. A stunt performer standing at the edge of a 10-meter high building jumps off and lands on a trampoline. Cool. The trampoline brings him to a stop at ground level. The intermediate situation, the trampoline then bounces him 5 meters in the air. The final situation, make sure that we are including air resistance. So why is this important? Well, air resistance is going to tell us that there is thermal energy. So if we go ahead and look at this, we see our guy right here. He's going to fall down. He's going to land on the trampoline and then come back up to this point right here. So what types of energy are present? Well, in the beginning, he has some height. So gravitational potential energy is present in the beginning. It says that his velocity is zero. So if he's not moving or he's at rest, there is no kinetic energy. Thermal energy. Well, thermal energy is energy that comes from friction or air resistance, and also it's energy that has been lost. We are not losing any energy at the beginning. So we can say that thermal energy is zero, or it does not exist in the beginning. And this will be the case for every single problem. Initially, you will always have zero energy. Elastic potential energy? Well, is anything stretched before he jumps off? No. He's just standing here, right? He's not wearing sweatpants, okay? He's not standing on a spring, so there's no elastic potential energy. Next is right here when he's on the trampoline. We notice that velocity and height are zero, so both of these are going to be zero. We notice that he is on a trampoline, and trampolines have springs, so he is going to have some elastic potential. And then we need to remember that it told us that there was air resistance. So that means that as he was falling, he was coming into contact with air resistance, therefore generating thermal energy. Lastly, we have his final spot right here, and we notice again that his velocity at the final spot is 0. So no kinetic energy, but his height is 5 meters. If he has height, he has gravitational potential energy. There's no springs or anything at this final position, so his elastic potential is 0. And then lastly, thermal energy. Well, if you have thermal energy in the middle, it's not going to go away. It's going to continue and get bigger and bigger as your problem goes on. So there is going to be more thermal energy at the end. We also know that he's going to have thermal energy because he's in the air and he has air resistance. So thermal energy is present at the end. Same question, but now we need to go ahead and find our energy pie charts. So it was good that we identified the types of energy on the last slide. So now when it comes to finding the pie charts, this should be a piece of cake. Initially, we said all he has is GPE. So in the beginning, all we need is GPE. In the middle right here, we said that he had elastic potential and thermal energy. So we need to find a energy pie chart that has both of those right here. And at the end, he has gravitational potential and thermal energy. He is at half the height, so he's going to have half the gravitational potential and half the thermal energy, just like that. So perfect. And like I said, as you can see, as this process goes on, his thermal energy gets bigger and bigger because he's losing more and more energy to air resistance. Now let's take a look at this question. This is definitely one of the harder ones on this quiz. It says the chart below starts at point 1 and ends at point 4. Label and draw pie charts and types of energy present, all that good stuff. Ignore friction and air resistance. So this is telling us right away that there is no thermal energy at all in this scenario. So I'm just going to go ahead and write no for all of these thermal energies because I know that if we don't have friction or air resistance, we're not going to lose any energy. So the first one tells us that the velocity is 0 at point 1. Well, that makes sense. So my kinetic energy is 0 there. I see there's a spring though. Because there's a spring and because it looks like it's being pushed, we're going to have some elastic potential energy. The other thing to note too is that we do have some gravitational potential energy. How do I know? Well, our cart has some height, and we can see that here. At the bottom, height is 0, so it can be assumed that anything above this point has height. Therefore, there's gravitational potential energy in the beginning. Number 2 is when we are right here and the spring is no longer touching it. So the cart is now moving and the spring is not touching it. If there's no spring, there's no elastic potential. If we're moving, there's kinetic. And then also we still have that height from our gravitational potential energy. Number 3, we're at the bottom, there's no height. So because there's no height, there is no gravitational potential energy. And then also there's no spring at number 3, so there's no elastic potential energy. Where did all of our energy go? Well, our cart is moving at this point. It's moving at point 3, so we're going to have a kinetic energy at point 3. Lastly, number 4, we're at the tippy top, and we have no velocity here. Velocity is 0, so our kinetic energy at the top is 0. But what do we notice? We have a lot of height up here at point 4, so our gravitational potential energy is going to exist. And then lastly, elastic potential. I don't see any springs or anything going on up here. So there are no elastic potential energies at point 4. All right, guys, so we just talked about this problem, right? On how in the beginning, all we had was GPE and EPE. So I just need to go ahead and find that graph down here. And I notice that it's just right here. Half of it's GPE and half of it's EPE. And again, this energy pie chart at this point in our curriculum is just a rough estimate. So it might not be exactly half, but it's right around there. And that's good enough for us. Number 2, though, we remember is the point at which the spring is no longer touching it, and all we had was GPE and KE. So I need to find a chart that has half GPE and half KE. That's right there. Go ahead and drop that. Number 3, we have no height. So if we remember, the only type of energy at point 3 was KE, and there we go. And lastly, number 4, we have no speed or no motion. All we had was height. So at number 4, all we need is GPE. And this is what our energy pie charts should have looked like for this problem. Next, we're going to talk about pendulums. And for this one, it wants us to look at this picture and use it to answer these questions. So at which point or points will the pendulum have the largest potential energy? Well, let's remember, potential energy depends on height. So when is this pendulum at its maximum height? Well, it looks like point A and point D have a maximum height. So this is going to be points A and D. And then our next question, at which point will the pendulum have the largest kinetic energy? Well, let's really think about this question. If at point A it has the maximum gravitational potential energy, when is it going to have the least gravitational potential energy? Well, that would be at point C. And what does that mean? Well, where did all that gravitational potential energy go for point C? Well, it transferred to kinetic energy, because we know energy can only transfer. So therefore, if at point C it has the smallest GPE, it's going to have the largest KE. So point C is going to be our answer for where this pendulum will have the most kinetic energy. And that's just telling us that at point C, our pendulum is going to be moving the fastest. And if we think about, right, Miley Cyrus' Wrecking Ball, if she came in like a wrecking ball, she would come in the most like a wrecking ball at point C, because that's when she would be moving the fastest. And then our last one, here's a spring question. It says, where is GPE the highest? Well, GPE depends on height, so obviously it's going to be at the top of our spring. So that's going to be when the mass is at the top. And where is EPE the highest? Well, EPE is either going to be the highest at the top, halfway down, or when the spring is fully extended. We know that EPE has to deal with stretching things. So this one's pretty easy, and it's going to be when the spring is fully extended, because it's fully stretched there. And the more we stretch it, the more elastic potential energy we will have.